what we'll do, and this, yeah, triple scalar product. Right, so one of the concepts is the magnitude of the cross product. And so that's actually fairly simple. Nice. It's actually fairly simple because it's related to a rule. And we'll talk about the justification of the rule in a few minutes. And we'll do a little proof. And then we'll go from there. So the magnitude of the cross product between two vectors is the dot product of the two, well, if you're multiplying two scalars, you're dotting them anyway. So the magnitude of u times the magnitude of v times the sine of the angle separating those two angles. Now, you may look at this problem and say, well, I don't want to use your fancy formula because I think it would be easier to just find the cross product and then find the magnitude of that result. And I would agree with you, but we need to kind of verify that this rule is going to work. So we're going to actually do it both ways. All right. So first we'll use our rule. All right. So we're going to have the magnitude of u. So we're looking for the magnitude of u cross v. I need the magnitude of u, the magnitude of v, and the sine of the angle between them. All right. So the magnitude of u. It's along the y-axis, so it's a clean 4. I mean, you could do the squared values added together and then take the root, but that's what it's ultimately going to end up being. All right. Then the magnitude of v, by the same rationale, is going to be 3, because it's along the z-axis, 3 units away from the origin. All right. So now we just need the angle between these two vectors. All right. We could solve for it. But if you have a good visual sense of what's going on here, then you should already kind of know what that angle is. But let's say you don't. All right, so cosine theta is equal to uv, the dot product of uv, over the magnitudes multiplied. All right, so I'm not going to really do much work here because the dot product itself is just going to be 0. All right, so as long as the magnitudes themselves aren't 0, then we're good. All right, that's why we say that if the dot product between two vectors is equal to 0, as long as one of those two vectors is not the 0 vector, then you're looking at an orthogonal relationship. All right, so I have cosine of theta is equal to 0. Now I could solve for the angle, but ultimately I want to find what the sine of theta is. All right, so theta would be equal to the inverse cosine of 0, but then I can take the sine of both sides of this equation and just write the sine of theta is equal to the sine of the inverse cosine of 0. All right. That's assuming you want it to be more of a calculator type problem. Right, so if I do that, then I'm just looking at 4 times 3 times the sine of the inverse cosine of 0. And again, something that's very, very calculator ready. All right, so you can look at it and say, well, cosine, where is that going to be equal to 0? That's going to be either at 90 degrees or 270 degrees. Right? Either way, when I take the sine of that value, that angle, I'm either going to get plus or minus 1. Right? So positive or negative 1. Since I'm talking about a magnitude is an absolute value. One way or the other, I'm coming up with a 1. Right? So the calculator may tell you that this result is negative 12, but you would drop the negative anyway. All right, so we're looking at a result of 12. So this magnitude of the cross product is equal to 12. All right. So we're going to want to start thinking about, okay, well, what does that mean? But before we get into that, let's talk about the other approach that you might consider using. Now, the other approach I think is more beneficial when the angle between the two vectors isn't easy to come by. In this case, I've been doing this a while. So I kind of know what to look for. You know, in theory, you're either there or you're getting there. When you look at, you're looking for the angle between two vectors, you look at the two vectors and see if they're going to zero out through the dot product. All right, so looking at the corresponding parts, if you multiply them, will I get 0? If the answer is yes, then you use this approach, all right, uv times the sine of theta. If the answer is no, then you would most likely use the other approach where you find the dot product between those two vectors, all right? So, sorry, cross product between those two vectors. So I'm going to find u cross v. All right, so we know it's going to alternate in sign, I, then negative j, then positive k. So for the I, it's going to be 4 times negative 3, so negative 12. So diagonal down minus diagonal up, so negative 12 minus 0 is just negative 12. So I'll just highlight that part. Now for the j and k, in either case, we're finding the determinant with a column that contains, well, it doesn't have to be both columns, but all it takes is one column containing all zeros. If that's the case, then the determinant for each of those parts is going to be 0. All right, so this boils down very nicely to just a negative 12i, all right, the magnitude of which, you do the work, but it's just going to be equal to 12, all right, so you'd get it that way too. So a little bit simpler, sure, but not always. All right, so I'll put a star on the next one. And then we'll talk about the area of a parallelogram, because that's all going to kind of tie together with the concept of the cross product. All right, so I have a diagram labeled up for you because I guess you got to start somewhere. If we locate vectors u and v such that they form adjacent sides of a parallelogram, then the area of the parallelogram is given by the magnitude of the cross product between u and v. All right, so area of a parallelogram is base times height. So the base of this parallelogram, well, the vector itself doesn't represent a length. The magnitude of that vector does. So the base is the magnitude of u. The height, I labeled it up here, but I do want to take a second and talk about where this is coming from. So I have an angle here, and this unknown side that I'll call h for height, right? Because I'm looking for base times height. All right, so ignoring the v sine theta, because that seemed to come out of thin air, what I'd be looking for is the sine of theta is equal to the opposite side over the hypotenuse. Now the hypotenuse, again, is a vector, but if it's going to be a length, it has to be the magnitude of that vector. So hypotenuse would be the magnitude of v. Now if I solve this for h, I get v, magnitude of v times the sine of theta. All right, so opposite over hypotenuse. All right, so let me turn this off. All right, and so that's where the v sine theta is coming from. Now if you chuck that into the formula for area of a parallelogram, you're looking at magnitude of v times the sine of theta being multiplied against the magnitude of u. So that is designated as the magnitude of the cross product of u and v. All right. So what this tells us is more of an intuitive understanding of what a cross product is really giving us. The length of the cross product between two vectors is equal to, by definition, the area of the parallelogram formed by the two vectors. And that would be the parallelogram that you would create in order to find the vector sum. All right. And so what that's getting at is the idea that it ties together nicely with the concept of area, right? Because determinants and areas represent the same thing. So a determinant of a 2 by 2 square matrix would be the area corresponding with that 2 by 2 square matrix, right? The determinant of a 3 by 3 square matrix would be the volume. So we extend it into the third dimension, the volume of the parallelepiped formed by the three vectors that make up that 3 by 3 square matrix, all right? So what this is telling us is that the cross product is in essence getting at that same idea, but we're not limited to just square matrices, all right? So if I needed to find areas on the plane, a two-dimensional, three-dimensional system, I could use this technique in lieu of the determinant, because if you're going to find a determinant, how are you going to do that if it's not a square matrix? So this technique is the workaround for that. This will be pretty much it. We don't need. So a couple of problems where we apply this concept. I'll do one of them with you, and then I'll start the other one. So it really doesn't matter because they essentially end up being the same thing. So I'll do the second one, so I'll start with the first one. All right, so we have the ordered triples. They're pretty convenient ordered triples, and I'm saying find the area of the triangle. And so you might be saying to yourself, well, wait a minute, you just talked about the area of a parallelogram. How are we supposed to know the area of a triangle? All right. Well, a couple of ways. One would be to just really modify the formula that we use for area of a parallelogram, because area of a parallelogram is base times height. Area of a triangle is base times height over 2. So just take what you would get for a parallelogram and chop it in half. All right? So area of a triangle is 1/2 the area of a parallelogram. The other way is more of a visual approach, but it really amounts to the same thing. It's really just a matter of taking the triangle that you have and replicating it to create a parallelogram, then finding the area of that entire parallelogram, and then chopping the result in half. All right, it amounts to the same thing though. All right, so what I need are some vectors. So I got to decide where I'm going to pin this. I'll pin it at P. So I'm going to get vector P to Q and vector P to R. So negative 1, 1, 0. And negative 1, 0, 1. All right. So I'm looking for an area, so it's a question of do I want to find the cross product or do I want to use the shortcut rule, which, again, doesn't always amount to being a shortcut. It's already in vector form. I can easily find the dot product between these two quantities, so that's what I'm going to do. It doesn't end up being 0, so we got a little bit more work ahead of us, but nothing crazy. So cosine of theta is equal to, again, u dot v over the magnitudes multiplied, but in this case it's pq dotted against pr and those magnitudes multiplied. All right, so the dot product is just a 1. The magnitudes are each radical 2. 1, negative 1 squared plus 1 squared plus 0 squared in both cases. Yeah, square root of 2. But then square root of 2 times square root of 2 is just going to give me a 2. Kind of interesting how this unit circle stuff keeps coming back again and again and again and again. You're supposed to have a quiz tonight, but I forgot to make copies of it, so it's not going to be tonight. So you're off the hook. So, and I have something. I got a full lecture plan for Thursday, so so we'll just do it next Tuesday. And there also is a bonus opportunity coming your way. I set a remind for it. I think it's coming out tomorrow, though. But it's another game, this time with tangents, right? Because that's what the unit circle quiz is. It's the unit circle, and then you also have to state the tangents all the way around the circle. And so that's what the game will do, too. Right? So another bonus opportunity. It's just, again, like I said last time, it's me trying to trick you into studying for the unit circle quiz. Right, so. What's that?
The quiz, it will be the same
as the last one?
Yeah.
No, because it's going to have the tangents around it too, right? So it's kind of a step up. But if you do the bonus that comes out tomorrow, you'll know what the quiz is basically. So cosine of theta is equal to 1/2. So unit circle values, but again, maybe you don't know it, so you write it as theta is equal to the inverse cosine of 1/2. And so the sine of theta is equal to the sine of the inverse cosine of 1/2. All right, we're looking for an angle between these two vectors. It's pretty reasonable to assume that it's going to be an acute angle. So, I mean, just by looking at the picture, you know, you can't always assume it's drawn to scale, but if it were obtuse, it would be pretty obvious, I think. So, you know, you're just looking for the sine value that goes along with the cosine value of 1/2 on the unit circle. And so radical 3/2 is always the companion to 1/2. It's just a question of whether it's positive or negative. So you pretty much have it. It's just a question of whether you want to include it yet or you want to include it in the next step, which is where we take our rule, which is the magnitude of the cross product of u and v, in this case pq and pr, is going to be equal to pq pr. Just, why can't I undo? Oh, that was weird. It just glitched pretty crazily. PR times the sine of theta. so each of my individual magnitudes are radical 2 times the sine of the inverse cosine of 1/2, which you could just chuck in the calculator if you want. But ultimately, when all is said and done, nothing left to say or do. So you'll have radical 2 times radical 2, which is 2, times radical 3 over 2. So it'll all come out to radical 3. Now again, the area of a triangle is going to be half of that. So radical 3 over 2 would be this area of a triangle. All right, and it all comes back to this idea here, that area of a parallelogram is twice that of the area of a triangle. So take the area of a parallelogram, chop it in half, and you have the area of a triangle. All right. But yeah, pop it all in the calculator if you want, but or use the cross product approach and then find its magnitude. But still, you'd have to chop it in half in the end. All right. Yeah. So then we get to the triple scalar product. Very, very intimidating sounding term. Actually, it just sounds like just taking terms from the course and just throwing them together at random. Triple scalar product. Nah, he's just making stuff up now. It's triple because there's 3 things. It's a scalar product because ultimately, in the end, even though you're going to have vectors to begin with, you're taking a dot product, which is also known as a scalar product, right? So 3 things multiplying through a dot product. So that's where the name comes from, all right? And the result is always going to be a scalar, right? So triple scalar product of vectors, this one, that one, and the other one, is the determinant of the 3x3 matrix formed by the components of the vectors, right? So I'm going to take you through this. It's not quite a derivation. It's more of kind of a, I'll say a justification. But I do want to show you the connection, right? So let me just have a purpose, right? You know, like, what's the point? You're like, yeah, I got another question right. I don't know why. All right. So, again, I'll pop this in my calculator. I'll get a very, I'm sure, impressive looking answer. Theoretically, we have a little sense of where these values are coming from, which is good. But we also would like to know, okay, that's wonderful. But why? Because there was a person somewhere along the lines that said, you know, it would be really cool. Take the cross product and then on top of that, multiply it by another vector using a dot product. If we do that, that would be really awesome. Like, I'm sure that, like, people would be lining up to date me after that. You know, like, I create that rule, like, they're just going to be beating down the door. Nah, it didn't really play out that way. They were already rich. They're like the people who came up with all these mathematical things that we're required to learn about now, they did so because they were already, like, incredibly wealthy. To the point, like, if you ever thought to yourself, like, whoever came up with this must have had a lot of time on their hands. That's what rich people have, a lot of time on their hands. And so some of them end up doing, like, what ends up putting them in the tabloids, and then some of them create triple scalar products, right? And so, like, they already had everything they wanted, and they're like, you know what? I want to better myself through the study of mathematics. You know, I needed a job, so that's why I do it. Yeah, so determinant. And again, still no idea why. Finding these determinants. Oh, -8. Ooh, fancy. I got my triple scalar product, which is, again, the same as the determinant, which, again, is a cross product followed by a dot product. All right, so now we got to be thinking about, all right, what does that do? So, the cross product gives, well, the magnitude anyway, the magnitude gives you a length that's consistent with the area of a parallelogram. But the cross product itself gives a vector orthogonal to two given vectors. All right, so I'm starting off with my two given vectors. I got one going this way, one going that way. That's my cross product. All right, that's easy enough. Now, we talked about the idea that the magnitude of the cross product is going to basically simulate a parallelogram. So I'm going to draw that parallelogram and give us the area. All right. Now, a dot product comes in different flavors, but we talked about the idea of projecting one vector upon another. So when you're finding the dot product between two vectors, you're finding really the component of one vector that's acting in the direction of the other. It's just a question of what your perspective is. All right, so what we're doing is we're taking this area, this bounded area, and finding the component of it that's acting in the direction of the cross product. All right, so we have all of these, like infinitely many vectors in this span that have some component acting in the direction of the cross product. And so what that does is it creates, for every one of those vectors, it creates height. Now, if I could draw it better, this would look wonderful, but I can't. If you come away from this being like, all right, it looks like a rectangular prism of some kind, then that's the idea, right? What it's really supposed to be is a parallelepiped, right? Which is why the technology assignments exists, because you experience what these graphs are supposed to look like as opposed to what I just constructed. Right? But what this is doing is it's taking the components of the area that's acting in the direction of the cross product and then aggregating all of those over the course of the span. Right? And when you compile them all together, just like volumes of cross sections in Calc 2, when you put all of those areas together, smush it all together, you create a volume. All right? So a triple scalar product is in fact giving you the volume of the parallelepiped that has those three vectors as its basis. All right. So the basis of the three-dimensional system, you're talking I, J, K. That would allow, if you create a linear combination of those three vectors, it would allow you to create a vector that would span any part of that three-dimensional system, all right? But I could never find the volume of a parallelepiped that has infinite length, right? Because it would have infinite volume, right? But if it's maxed out in a certain, at a certain length in any direction, then I can make a determination of what that volume is going to be. Now, if those vectors are along axes, that's easy, length times width times height. But if they're going off into weird directions, that makes it a lot more challenging. So this concept allows us to very easily come up with those volumes very quickly and easily, all right? So anytime they're asking you to find the volume of the parallelepiped, they're asking you to find the absolute value of the triple scalar product, which is the same as saying find the determinant and drop any negatives that might be there, all right? So number 11 and number 12 just got a whole lot easier. Although number 12 is impossible if you have no idea what the word coplanar means. Oh, sorry, this is me not telling you what coplanar means. All right, so vector spaces and subspaces. This is more proof-based stuff, still more theoretical things, but we do need this in order to really get into the application stuff. So a lot of this is a rehash of stuff that we already knew. All right, we know what a vector is. We know what a vector space is. All right, so vector space, any kind of linear combination of vectors. All right, addition, scalar multiplication. All right, and all of these properties apply. All right, so what happens is we have real space, which is really just us spanning through a real number system in 1, 2, 3, 5 dimensions, doesn't matter, just with numerical values. But what vector space does is it allows you to span through real space using vectors as your basis. All right, so it's just another way of saying a linear combination, because if I'm using my vectors as the basis of that space, then I can define any movement in that space based off of its relationship to the given vectors. All right, so I, J, K are our standard unit vectors for three-dimensional systems, so I redefine everything in terms of I, J, K. All right, but what if I wanted to change my basis? So instead of I being 1, 0, 0, I is 1, 2, 1. What would my movements look like in that reality? That's something that we're gonna have to play around with. But for now, we're just gonna make a determination of whether or not something is considered to be a subspace of a given vector space. All right, so we have our properties. The properties I think are pretty standard, but the subspace, definition of a subspace is if the conditions are met, W is called a subspace of a real vector space V if W is a subset of the vector space V, and W is a vector space with respect to the operations in V. All right, so all more varied ways of saying linear combination, but the conditions are really where we want to kind of live, because this is how we're going to verify whether a vector represents a subspace of a given space. All right, and when we talked about span back in the first unit, we're really just talking about the idea that, okay, so sometimes a vector may not be in the span created by 2 other vectors, 3 other vectors, whatever it is, all right? So that span corresponds to the subspace, all right? If you span out to the entire real number system, then it's not a subspace, that's the vector space itself. But maybe, for example, just to keep it simple, if you're dealing with just 2-dimensional system X, Y, your subspace could just be the first quadrant, all right? Because it's just a subset of the original system, all right? X going from negative infinity to infinity, and same thing for Y, all right? In order to be a subspace, the 0 vector has to be in it, all right? That's the easiest thing to test for. and it's also kind of like from a student perspective, your best friend, because if it's going to fail, to be a subspace, it's probably going to fail in that step, right? And if it does, that means everything else is irrelevant, and that's good news. U and V are any vectors in W, then the sum of those two vectors would be also in W, all right? So it would be a closed system. We talk about, and I do enjoy the symmetry of it, in Algebra 1, in my high school Algebra 1 class, 9th graders, we talked about real number systems, but we're talking about just like integers, whole numbers, and stuff like that. But we do talk about a concept of closure, you know, having a set be closed under a given operation. So if I say that a set is closed under addition, that means that if I'm given a set of values, that I could add any two values and the result would be in that given set. Like for example, whole numbers. I could add any two whole numbers and still get a whole number as a result, right? But the set of whole numbers is not closed under division, right? Because if I divide any two whole numbers, the result is not necessarily going to be a whole number. 2 divided by 3 is not a whole number, right? It's the same idea here. I'm looking for closure. I'm looking for U and V that are already vectors in W to be closed under the operation of addition, meaning their sum has to also be in the set of W, in this case, whatever that real system, vector space is. If C is any real number, so a scalar multiple, and U is any vector in W, then the scalar product has to also belong to the vector space W. All right, so those are the things we're looking for. So what does it boil down to? Proving a linear combination yet again, right? Just using different vocabulary. So guided example. And then I got a bunch that are not guided. So it's pretty straightforward when you're given general terms, because there's really not much to do. So I need to verify that my sum is going to be in the vector space W. My scalar product is going to be in the vector space W. But even before I do that, I want to make sure that the zero vector is going to be a possibility. All right. And so all I'd have to do is make a statement that as long as A1 and A2 are equal to 0 or can be equal to 0, I'll be fine. All right. So unfortunately, that means that you go the distance for a question like this, but that's not terrible because there isn't really much to do. All right. So if A and or A1 and or A2 can be equal to 0, then the 0 vector is accounted for. If I add these two numbers, assuming that A1 and A2 is some real number, the result will also be a real number. Scalar product, multiply C by U, it's going to be in the set of W. All right, there's no reason to think it won't be. All right. So it's pretty vague, but it kind of gets the mechanics of the concept across. And the same thing with the next one. You know, it's just expanded up to omnidirectional and, you know, dimensional. So you can go up to n by n. So, but it's basically saying the same thing. But on the next page, we get into one where we have to kind of do it ourselves. And this is a little bit more interesting. All right. So again, we're defining W3 as the subset of real space 3. All right. So vector space W, vector space where W is in 3 dimensions, is part of the real number system in 3 dimensions, consisting of all vectors in the form of A squared, and B. All right. All that's telling me is the form of it. So whatever my first entry is in the vector, the second entry has to be the square of that. All right. So if this is 2, that's got to be 4 necessarily. There's no choice. If that's a -1, that's got to be a +1. Right? B could be anything though. All right. So first thing I would want to do is verify that the 0 vector is a possibility. All right. So can the zero vector be in W3? All right. And so the way I would do that is just very simply taking my given vector and setting it equal to 0. All right. So yes, if A is equal to 0 or B is equal to 0, or and B is equal to 0. That's the only way to have a zero vector. All right. But it is a possibility. So let me just give you a quick what if scenario. Let's say, I would say, what if this were, the second entry were A plus 2? Then you would start thinking, well, in order for this to be the zero vector, A would have to be equal to 0. But if A is equal to 0, then the second entry would have to be 2, because 0 plus 2 is 2. Then it would show that there was no way that the zero vector could be in the set. Because even if I were to, like, if this said A plus 2, and I let A equal -2, then that would force that one to be -2, just to make that one a 0. So it would all fall apart. All right, so it doesn't take much to find a scenario where it doesn't play out. In fact, I might make that an example in a second. All right. So we've satisfied the first condition, which is, academically fine. As a student on a test, it's not what you're hoping for. All right, so now what I'm going to do is I'm going to find the sum of any two vectors in this system. All right, well, they're vectors in the form of A squared, and B. All right, so I can make anything I want. So how about I let U equal A sub 1, A sub 1 squared, and B sub 1, and V be all that same stuff, just with sub 2's. And so I want to know if the sum of U and V is going to be in the set, the vector space W3. All right, so I add them together, and I see. So U plus 3, U plus V. I don't even know where I came up with that 3. And I would say that this is probably the hardest part of a question like this, or relating to the concept, is that you get this and you say, all right, yes, no, did I do it? What does this tell me? Did I get the answer? Do I have an A? Well, you got to go back to what the form of W3 is. The form of W3 is any vector that has the first entry squared giving the second entry. All right? So the question would be, is this in that form? All right? So is that in the form of W3? And so I would need this entry squared to give that entry. So is A1 plus A2 squared the same as A1 squared plus A2 squared? And the answer is only if there's zeros. All right, so that's a problem, because we need it to always be the case, because these are general terms. So Not always. Therefore, do we have a name for this? No, so we're going to say the vector is not a subspace. Of W3. So if that checked out, if we got this relationship to be true, because B1 plus B2, that we don't really care about that one because B was a unique value, it wasn't related to anything else in the vector. But if this checked out, then we would check scalar multiples and see if that ended up giving something that made sense. We usually save the scalar multiple case for last because that almost always checks out. So, you know, if it's going to fall apart, it's going to fall apart in this step, right? So that's assuming you get past the zero vector concept, all right? So I'll create that side example that I was talking about. Yeah, I'll just say off on the side here, what if dot, dot, dot. So let's say it was in the form of A plus 2, and then I'll just keep it simple, B. All right, for this one, we wouldn't even get past the first step, all right? Because what I would want to know is 0 in the set of W3. Does 0 belong to the set of W3? All right, so if that's going to be the case, then what I would do the exact same thing I did before. I would take my A plus 2, and B, and set it equal to 0. So in my first computation, well, it's not even really a computation, I get A equals 0. For the second one, I get A plus 2 equals 0, which means A is equal to -2. Well, A can't be two different things at the same time, so this is a contradiction. So the vector is not a subspace of W3. All right, so another little instance where things start to kind of fall apart. All right, but it falls apart in different capacities. It's a question of, does it fall apart because of the zero vector, because of the vector sum, or because of maybe a scalar multiple? All right, scalar multiples are kind of trickier to come up with examples off the fly, but basically anything that would lead to a contradiction in value is something that would kind of fall into that category. All right, and anything that involves maybe a transcendental function, you throw in a trig function and it tends to upset the apple cart pretty easily. Right, so. Oh, that writing is huge by comparison. All right, so I'll put a star on the next example for you. It's just kind of getting at the same idea, just in a slightly different way. All right, so null space, column space, dimensions, rank. All right, so these are characteristics of subspaces. So more terminology and things like that. Some of these things the calculator does, and some of it we just have to do by hand. Some of it is related to things that the calculator does that we just kind of have to interpret things that we already know how to do on the calculator just in a different way. All right, so the null space of an n by n matrix, written as null A, right? Linear algebra notation can be weird. It's like, what kind of abbreviation is that? What
Is that a typo bonus?
no, I mean,
Yeah,
that's,
that's real.
yeah, that's actually what the notation is, but like, it's not like we're going down from logarithm to log. We're going down from null with 2 L's to null with 1 L. Like, come on, man. I know why. It's because they made column space call, and they want it to be consistent with the number of characters. But it's just, I mean, at some point, you just gotta kind of move away from being so particular about structure that, whatever.
But span is 4.
Yeah, I know. I think the only thing I could come up with is that they didn't want it to end in a vowel either. Because if you had spa and then spa A,
Can we do NL?
yeah, they really could have done anything. Like anything other than what they chose to do.
Oh, potato.
Yeah, the potato A.
Potato.
Ah, yes, that's true. Then we'd have that conversation. It's pronounced potato. Yeah, so it's a set of solutions of the homogeneous equation AX equals 0. So it's like, wait, what? The null space of an n by n matrix A written in this form is the set of all solutions of the homogeneous equation AX equals 0. All right, so if you're rightfully thinking, wait, we've done this already. You're with me. Yeah, we have done this already. We're just giving it a different name, and we're going to use it for something else. All right. So in our set notation, we write null A, and then x such that x is in R n, whatever that space is, and A of x equals A times x equals 0. So basically, what this is getting at is the variable and the condition related to the variable. So what is x equal to? Right. So all you're doing is representing your parametric form of your linear system AX equals 0 matrix equation. All right. So our theorem. This is why it's important. Null space of an M by n matrix A is a subspace of real space n. Also, the set of the solutions to this system AX equals 0 of a homogeneous linear system in n unknowns is a subspace of Rn. All right. So what this is telling us is that it is guaranteed that the solutions to a homogeneous system will be a subspace of the real number system. All right. So it's taking something that we already know and kind of merging it with something we're just learning about. Now, column space is a set of all linear combinations of the columns of A. All right. Also talking about the span. Now, when we talk about the column space of a matrix, what we're talking about is the relevant columns or the minimum number of columns necessary to create a span for whatever the system is that you're dealing with. All right, because let's say, for example, you have a 4 by 7 matrix. All right, so 4 rows, 7 columns. All I need are 4, if I have 4 rows, all I need are 4 columns in order to span out 4 space. All right. So that's telling me that I'm going to have 3 extra columns that are unnecessary. Right? They're just extraneous. So it's just really asking me, well, which are the ones that I really need? Right? And which ones can I get rid of? Right? That's what the column space is talking about. And this is really, the theorem is just really kind of getting across that idea. The dimension, right? So the dimension of a vector space is the number of vectors in the basis for V. All right, so that's going back to column space. So the number of vectors that form a basis for your vector space. All right, so again, if I have a 4 by 7 matrix, I only need 4 of those columns. Those 4 vectors make up the basis of 4 space. So it's a question of what those vectors are. Well, I know what my dimension would be because I would have a need for 4 vectors, so my dimension is going to involve a 4. But those 4 vectors form the basis for 4 space. All right. If I had a 5 by 9 matrix, I would need 5 columns in order to get that same job done. All right. We've been kind of living in the world of 2 by 2s and 3 by 3s, And so what we're trying to do is kind of get across the idea that everything we know about 2s and 3s can be expanded to higher order dimensions. And it's just a question of really just taking the necessary components and working with it. So dimensions of null space A and column space A. Dimensions of null A is the number of free variables in the equation, and the dimensions of column A is the number of pivot columns in A. All right, so I think that would make sense, because when you're talking about a pivot column, you're talking about the variable that you're solving for when you actually rewrite your solution in parametric form. Okay, so I would have maybe a pivot if I had 4 variables. If I had a pivot in 3 of the columns, that's telling me that one of the columns is going to be associated with a free variable. Right? So now I indirectly know what my null space is going to be related to in terms of free variables and the number of columns. So the sum of those 2 values should actually give you the total number of columns in the matrix. All right, so really, I mean, again, the dimensions of null in column A, column space of A. Dimensions of null A is the number of free variables in the equation. Dimensions of column space A is the number of pivot columns in A. All right, so really, it's all the same. We've been doing this the whole time. It's just we're talking about it in a different capacity. All right, so we have A and U, and they're asking us to determine if U belongs to the null space of A. All right, so again, null space is a solution to the homogeneous system. I would need to make a determination of whether or not that falls into that solution. So let's solve the homogeneous system. So AX equals 0. Alright, so with my ref, I'm getting this good looking solution. All right, so I could write this, I mean, there's an implied x here, even though I wrote ax equals 0, I didn't show the step of defining my vector x equals x1, 2, and 3. So you're kind of hand waving around it, but this is really the same as saying x1 minus x3 equals 0. x2 plus x3 equals 0. And then we have the free variable x3 equals x3. So we're looking at x1, 2, and 3. Everything's going to be a multiple of x3. So add the x3 in the first equation, I'm going to get a coefficient of 1. Subtract it in the second equation, I'm going to get a coefficient of -1. And it already has a coefficient of 1. In the last one. All right. And so now at this point it should just kind of pop off the screen at you, where we're asked to determine if U belongs to the null space of A, right? So this is the solution to the homogeneous system. Any scalar multiple of the vector, the base vector 1, -1, 1, because 1, -1, 1 forms the basis of the solution. Any scalar multiple of that is going to be representative of that null space, all right? So now I don't have any other values here, so I don't have to really worry about linear accommodations coming into play, in a more expansive context. Like if I had like 4 or 5 different free variables, it could be kind of tough to figure out if U falls in a set, but U actually is what this would be if x3 is equal to 1. So we could say that U is in the null space of A when x3 is equal to 1. All right, not always going to be that easy, but never going to be that hard. Once you come up with your solution, most of the time it's just a matter of saying, oh, that's 10 times what U is equal to, or 1/3 of what U is equal to. You'll see what the scalar is, and it's pretty easy to just kind of pop that off. All right. All right, so for the next one, we got to do a couple of things. We got to find the column space, and then we also have to find the null space of A. But really, it's just going to boil down to the same process, because we need pivots. All right. So if I wanted to, I could go back into the first example and identify the relevant columns that form the basis of this system. All right, because I had 2 pivots. The first column and the second column had the pivot entries in it. So my first 2 columns of the matrix would actually form my column space. All right, so that's actually pretty easy. So if I wanted to, they didn't ask me to, but I could actually kind of off on the side here say that the column space of A would be the set containing the vector 2, -3, -5, and the vector 6, 2, -4. And again, the only thing I needed to do in order to figure that out was identify where my pivots were and what columns those corresponded to. All right, so those pivots correspond to the first and second column in the given matrix. So I have it. So what does that tell me? Well, rhetorical question. It tells me that I don't have to do anything different in order to find the column space, right? Because it's going to come out in the solution for finding the null space, all right? So I'm really just, in both cases, when I'm looking for a column or null space, I'm using the process I would use in order to find the column space, the null space, and then just kind of pulling out the column space from there, all right? Unfortunately, because we're spoiled now, it means that we got to type a new matrix into our calculators. But if we always keep in mind that the alternative is to do all this crap out by hand, it'll help you sleep at night, I guess. All right, it's a homogeneous system. Just doing a quick double check of Ruski here. And there it is. Just do a little copy paste. All right, so there's my R ref. We're looking for that's funny. I entertain myself sometimes. I just had this moment where I was like, crap, I screwed this problem up because I saw the what is K. And I'm like, there's no K in there, what did I do? And then I realized I forgot my own question. It's a subspace of R, K. You're like, what dimension am I working with? Right? So the column space, again, represents the basis of the system. So it'll tell us how many vectors we need to define our system. So what I'll do first is I'll identify the column space using a marker. So the column space of A is going to be the original vectors associated with the pivots. So I got a pivot right, meow, meow, and meow. So 3 meows. And so that's going to correspond with the one right, meow, meow, and meow. All right. Again, I need a marker, not a highlighter. So I write the original vectors, not the row reduced form. All right. So I needed 3 vectors to span this real space. All right. So the column space is a subspace of some real space. I needed 3 vectors. That means that I must be working in 3 dimensions. All right. So therefore, K is equal to 3, giving us real space in the 3rd dimension. All right. Now, generally, the number of rows will dictate the column space, or the number of vectors that make up your column space. The problem with that, relying on that relationship, is some of the sneakier questions that you can kind of see when you're dealing with row reduction. Like, what if one row is just a scalar multiple of another? It's not a unique equation in your system, right? So it didn't even need to be there to begin with. So you could have like a 5x5 matrix, but maybe there's only 2 unique equations in there because 3 of them are just repeats of the other 2, the 2 base equations. So we got to be careful about that, which is why we do the row reduction technique to begin with, right? So now the null space involves us coming up with a solution of the system. All right, again, we're solving AX equals 0. It's very easy to just hit R ref and write down some numbers. You always want to keep in mind what the point of it all is. All right, so X1, so I have 4 variables that I'm working with here. So X1, 2, 3, and 4 is what I'm up against. So X1 is going to be equal to -9 X3. X2 is equal to 5x3, and x4 is equal to 0. All right, and so we know that x3 has to be the free. So x1, 2, 3, 4, I'll just write x. It's going to be x3, and we're looking at -9 for x1, 5 for x2, 1 for x3 because x3 is equal to x3, and 0 for x4. All right, and so that is my null space. And that's probably the best way to do it. So this is Now, I just want to highlight something for you. We were indirectly finding these values all along. So if I wanted to find the dimensions of the null space, really it's just, well, how many free variables did I have? One, right? Number of pivot columns, how many vectors made up my column space? All right, so in this case, I could say that the dimensions of my null space would be 1 and 3 respectively. All right, the reason I bring that up, well, aside from just teaching it, is because I was about to put a star on number 3, and I realized I hadn't talked to you about how to find the dimensions yet. I mean, I talked to you about the definition, I didn't talk to you about how to actually apply the definition. All right, so row space and column space, and rank, row rank and column rank, it's all pretty straightforward stuff. It's just procedural. So we've already covered this. It's just a question of like the vocabulary. Row equivalence. This is kind of weird. This is a matrix B is row equivalent to matrix A. It's just like awkward, but I can't think of any. I'll take it as a typo though. Maybe any matrix B. Yeah, I'll write it that way. Because it kind of looks at first glance like it's somehow supposed to be matrix A, but it's not. So I'll say any matrix B is row equivalent to matrix A if B results from A via elementary row operations. All right, so that's something we knew about from way back when. That's what row equivalence is talking about. It's a scalar multiple or any other elementary row operations, then we're defining that as row equivalence, right? And that's really getting at the idea of those extraneous equations that make up a matrix, right? So if you're looking at a row equivalent, a matrix that's row equivalent to another one, then it doesn't necessarily have to be there, all right? So if A and B are two M by N row equivalent matrices, then the row spaces of A and B are equal, all right? So what we want to do is find the bases, right, of row and column spaces, all right? So this is it's process. So it's not bad, and the first step in the process is something you're very familiar with, reduced row echelon form, so row reduction, all right? The non-zero rows of matrix A in reduced form give, well, okay, so forgot to put matrix A, but I guess it doesn't matter. Non-zero rows of the matrix in row reduced form give the basis of row space, the row space of A, the non-zero rows, all right? The columns containing the pivots, those give the basis of the column space of A, all right? Now, we've been learning about column space really all along because we've been defining our matrices as being, the columns of those matrices as being the vectors related to, whatever space we're working in. But the reason why we talk about row space in addition to column space is because basically when we're talking about the cross product, we can represent a matrix using the rows as the vectors as opposed to the columns. All right, so we can say vector 1, 3, 2 as a row of a matrix as opposed to the column, and if that's the case, then certain rows would form the basis of that system as opposed to the columns. All right, so what we want to do is we actually want to know what the row and column rank are. all right? The dimensions of the row space of A is called the row rank, and the dimensions of the column space is called the column rank, all right? The row rank and column rank of the m by n matrix A are equal, all right? Since the row rank and the column rank of m by n matrix A are equal, we only refer to the rank of A, and we use this notation, all right? It's important to understand what a rank is talking about, but again, I mentioned this throughout the entire course, the vocabulary is what's gonna get you, because we're talking about the same thing over and over again, but just using different terminology. The rank is just talking about the relevant number of vectors necessary to define the basis of a system. All right, so if I'm in 3 dimensions, the rank of my matrix better be 3 if I'm saying that the vectors that make up this matrix define the basis of that system. Because if they don't, then what am I doing? You know, what's the point? All right, so we want the rank to be consistent with the number of dimensions that we're working with. So if we're in the 4th dimensions, I want the rank of the matrix to be 4. Right? But the good news about this is that all I really have to do is figure out the dimensions of either the row space or the column space, and I'll have the rank of the matrix. All right. So then we have this statement here. I'll take it as a typo. I think I didn't tab it over the right way. I think I put it in as a table. If I just shift this over a little bit, then the then would fit there, and it would look a lot nicer. So for this typo, I would say just submit bottom of page 77 reformat. All right. I start to get the idea as as we progress through the course, that when I talk about the typos, like a good percentage of the class has no idea what the hell I'm talking about, because I keep saying these typos and then nobody ever submits them, and then the corrections don't ever get made. You've submitted, but you're maxed out.
That was the question.
Yeah.
You get 3, right?
Once you get your 3, you're done. So, like in the early part of the semester, I get a lot, and then all of a sudden, it kind of fades out from there because people get their max. But I don't have a lot of people maxed out in this class, right? So odds are, and especially this is a pretty dense course, that there are other classes that you're probably taking that if you had an opportunity like this to submit typos, you whip out the phone and you submit it right away, and you wouldn't miss anything. Here you kind of miss an entire concept if you do that. So, but I can tell you that if you submit the typo, like even when you get home, if you submit the typo, just make a note, submit it when you get home, odds are you're gonna be one of the first people to submit it. And then you'll get the bonus, and then, once you get your 3 points, you're done, you don't have to worry about it anymore. But you could still continue to submit, because, every class, I point out like 3 or 4 of them, right? So 16 weeks, twice a week, 32 classes-ish, I'll bring it down to 30. Let's say 4 times per, that's 120 typos. And those are the ones that I recognize. It's the ones that I don't recognize, those are the ones I'm worried about. Because, this is a true story. I only learned like 2 years ago that IT' does not mean that something belongs to it. Like its shoes. Like I thought that like if I wanted to say, like Billy, no, that doesn't make sense. The dog and its bone. No. Apparently it means it is. What the hell? I've been living my whole life that way. And commas, I'm a fly by the seat of my pants user of a comma. Like this is really how it goes. I'm typing, and then I'll be like, yep, feels like a comma moment. Put that bad boy in there and move on. Right? Or my other train of thought is, haven't used a comma in a while. Feel like I'm due. Put one of those in there and hope it doesn't underline it in some weird color.
I'm convinced that the comma usage has changed in the last 15 years. Because in English class here, she completely rerouted my entire way of thinking about commas. I'm like, this is not how I was taught the first time around.
I just thought it was like,
They changed their mind, something happened.
maybe, yeah, that makes sense because, like, I feel like somebody along the way told me that, like, when you're reading something, if you stop to take like a full breath, that's a period. If you stop and take like a half a heartbeat, that's a comma. And then just kind of guess for a semicolon.
Eventually it was, right?
Yeah. I knew it was like two complete sentences that you, for some reason, want to put together. But then I always thought to myself, well, why can't I just make two complete sentences and just do it that way?
Yeah.
You know, I've never seen a semicolon that I've been like, yeah, absolutely.
Yeah, that seems like a perfect usage of a
I thought of it as like when you can place a because or and statement or something like that.
Oh.
Or place like that, but it wouldn't sound weird. I could place
Kind
a
of like a
semicolon.
therefore.
Yeah.
Yeah, I might just use that. I think that works because there have been times where I've been like, I got a 50-page packet here. I didn't use a single semicolon. All right, let me just jack two sentences together and put a semicolon in there. And then people will be like, that's not how you use it. I'm like, well, sue me. I don't know. I don't even know semicolon. So, but yeah, colons I think I'm pretty strong with. So, the dimension of the column space, which is also the same as the dimension of the row space, we call that the rank of the matrix. It's always going to be easier, I think, to identify the column space and therefore the dimensions related to the column. So column space, and so therefore the rank should come from that. Row space, I mean, you got to actually solve a homogeneous system in order to do that. For a column space, all you have to do is row reduce and find your pivots, all right? So it's a lot easier in that regard. The nullity, now I'm just making up words. The nullity is the dimension space, the dimension of the null space, all right? So if you know what the general dimensions are for, or the overall dimensions are for the matrix, once you identify the rank, then you have the null space because they have to add together to give you n, all right? So n is the number of columns. If you have 7 columns and only 3 of them are pivots, then your nullity has to be 4, right? Because it's got to be the remaining ones. Because all 4 of those would be related to free variables in some capacity, all right? So the nullity of A, again, is the dimension of the null space. What people have struggled with in the past, aside from just generally having to know lots and lots of words, is the column space seems to have a counterpart that would naturally be row space. You think columns, rows, column space, row space, but then all of a sudden it's column space, null space. And it's like, okay, you just threw a curveball at me. Like, why is this going on? Why is this happening? But I've always thought of the row space as just what I would do if I represented my matrix as having, instead of columns representing vectors, the rows are vectors. Like, I'm just changing my perspective. So very rarely am I looking for the row space, all right? Because generally I'm representing the columns of my matrix as the vectors of that matrix, all right? So find the bases. It sounds weird when I say bases, I know, but I really emphasize that because when I say bases, people, for whatever reason, have no idea what the hell I'm talking about. But when I say bases, they're like, ooh, wait a minute. That sounds a little bit like basis, all right? So it's the plural of basis, all right? So if I have the basis of a system, the bases would be, you know, like, am I talking about 1 vector, 2 vectors, or 10 vectors? Give them all to me, all right? So I want to find the vectors that make up the basis of this matrix, also known as bases, and the rank of the row and column spaces for A, given that matrix. So it's basically just taking everything that we've been covering and putting it all together. So with that in mind, you get a nice juicy star for each one of those bad boys. And then I encourage you to read through the important results on the bottom. and study them. Oh, look at that. That's a typo for somebody. This is from the old textbook. That shouldn't be there. I missed one. All right, and so that's pretty much where we're going to leave it for tonight. Next class we'll talk about, just kind of putting a ribbon on this, the idea of bases, and we're going to get into the concept of change of bases. Right, so it's kind of altered reality. So it's when things are going to start going from bland, dull memorization to a little bit more interesting. So we just had to kind of plow through this stuff.